I'm back. We had to go outside and enjoy the snow. So before I get into integration by parts, I thought I'd show you some of what we were doing today. Ready? Here is my house with the pretty snow. Here's a picture of Delaney sledding down our hill and me standing outside. And then I thought you'd like to see some of our sledding experiences. Here's Devin.
All right, Delaney.
Oh, no, sorry, Delaney. There she goes.
Oh.
That's Delaney sledding. And Devin is a little different. She's a little bit of a spaz.
I don't know.
Mr. Getz is filming, so it's a little blurry. The crazy kid. Dylan. Also crazy.
Just hit the side of it.
That's Dylan, and then Mr. Getz gets on our 1950s little steering thing. Looks like a dwarf. Fail. Here he goes again. So I hope you got to go out and have some fun today as well. But it is time for integration by parts. So as I told you in the email, you will have a book assignment for tonight. It's there on the screen. And our unit test is on Thursday, the 10th. I think I said the 6th in the email, but I meant the 10th. Sorry about that. So integration by parts is for taking the integral of a product. When you can't unproduct something. We use U substitution with products sometimes, and that gets us out of using the, dealing with a function, an integrand that's a product. Also, we can multiply stuff out sometimes and get rid of a product, but when you can't, when there's nothing to do and your integrand is a product, you need to try to see if you can use something called integration by parts. It is a little bit of a dagger because it is manipulating. You are really forcing a scenario and it doesn't always work. But to integrate a product, I have to remember not to just take the integral of each separate piece. So first I'm going to prove it. I'm going to prove why integration by parts works by starting with the product rule for derivatives. The derivative of a product, two functions, u times v, is the first function times the derivative of the second, plus the second function times the derivative of the first. So we've been doing that for a while. You recognize this. If I cross out all the dx's, because I do have an equation after all, and I'm left with no fractions, notice that over here I still have derivatives. I have a derivative of this product here and a sum on the other side. Now I'm going to do just some algebra 1. I'm going to take this and move it to the left side. See? Then I'm going to switch using the reflexive property of equality. I'm just going to take the u dv, put it on the left side, and all of this stuff, and put it on the right side. Now I'm going to integrate both sides. So if I integrate the left and integrate the right, I have on the right side the integral of a difference. The integral of a difference is the difference of the integrals, so I just now have two integrals on the right side. But notice what happens here. The antiderivative of a derivative. Hello, inverse operations, and goodbye. So I now have the integral of a function u with respect to v, which is a little awkward, is equal to the product of those two functions, u and v, minus the integral of the function v with respect to u. Again, a little awkward. This is, however, called the integration by parts formula. Of course, integration by parts is a little long, so we can call this IBP. Or you know me. Don't know how many of you are familiar with 90s rap, but this always reminds me of Naughty by Nature singing OPP. You know me. Just a little history for you there. Musical history, if you will. Didn't see that coming now, did you? So, using integration by parts, some things to think about. The u function, because I have to choose when I have a product of two functions, doesn't come with u and v. I have to figure out who are u and who are v, who is v. That's done by looking at both functions and deciding if the one of the functions can differentiate to 0. And I'll tell you what that means in a little bit. And the rest of the integrand needs to involve a function that is easy to integrate. You can kind of think about the integration by parts formula, or again the IBP, or you know me, is kind of sort of the product rule for integration. The most awkward part, as I said, is this choice of which function should be u. That is the first step in doing integration by parts. And so there's this little rule that we use, lipit, as a suggestion. It works most of the time. It's not a mandate, it doesn't work every single time, but most of the time, if you're looking at your two functions, and yes, Devin? Excuse me. What's up?
Can you put these into, are these like heatable?
Yes.
Like ovenable?
Ovenable?
Yeah, like put it into an oven.
I don't know if you can put it into an oven. You can put it into a microwave.
They're the same thing.
Here, let me see. She didn't want to say hello, did she? Oh, by the by, check out my coffee mug. Yeah. Cool. Anyway, so choosing u in this order. Lipit, where L stands for a logarithmic function, I for inverse trig, P for polynomials, E for exponents, and T for regular trig. Now this seems a little weird because usually polynomials are one of my favorite functions of all time in math, followed closely by exponentials because, let's face it, exponentials, e to the x is its own derivative and antiderivative, and I've always loved trig. So curious that these are at the end of the list when I'm considering functions for u. And logs being first, that seems a bit weird. Logs, inverse trig, polynomials, exponentials, trig. So here's my example. First example. Now I dramatically put the multiplication sign there, which normally wouldn't be there, right? You would normally just see this as x cosine x, and you would have to avoid the temptation to just say, oh, the integral of x is blah, the integral of cosine x is that, and I'll just multiply those two results. You can't do that. The integral of a product is not the product of the integrals. So, can I use integration by parts in this? So I look at the two functions separately, x and cosine x, and I go through my list of lipit. And I think to myself, I need to choose a u, and then everybody else is dv. I'm going to differentiate u, and I have to integrate the function in dv. Finally, I substitute, And hey, why isn't this step 5? Not till the end do I actually integrate, and if it's an indefinite integral, I put plus c. So first, are either two functions logarithmic? No. Are any of them inverse trig? No. But x to the first is a polynomial, so this is going to be my u, and all the rest is going to be dv. So I am going to write my integral to match the left side of the integration by parts formula, because by proof it will then be equal to the right side. And what we're trying to do is break this integral into parts. One part that has just a product of two functions, and the second part, which hopefully if we line everything up right, is a nicer integrand, something that I can actually integrate as opposed to x times cosine x, which I can't integrate. So I write down u and dv, I differentiate the u, and the derivative of x is 1, and I anti-differentiate cosine x. Again, you're taking the integral here, and the integral and the antiderivative and the derivative by, and I'm left with v is equal to the integral of cosine x, which is sine x. Now I'm going to substitute. Since I was able to rewrite my original integral to match this form, I can now rewrite that as uv minus the integral of v du. Multiplying x times sine x shockingly gets me x sine x. And then integrating sine, remember the formula has this minus. When you anti-differentiate sine, you get negative cosine. So negative cosine is where this positive comes in. And this is my answer. If you doubt me, take the derivative. Differentiate x sine x plus cosine x plus c. And I promise you'll get x cosine x. I hesitated to jump right to this next example, but I wanted to, because it's kind of outside the norm, and I've been integration by parts, look for a product of two functions, and this is obviously not a product. However, I alluded to the fact in the warm-up on Thursday that you don't have a formula. Integrating ln x is not on your formula sheet. You don't have a straight up, oh, the integral of sine x is this, the integral of cosine x is this, if I have x to the power, I power up, divide by the power up. The integral of ln x is not on there. You don't have a, just a nice formula for it. But I can anti-differentiate it if I'm kind of clever and force myself into a product where I have ln x times 1. Oh my gosh, teenagers in the house. I'm going to integrate u dv, which is equal to uv minus the integral of v du. Notice that ln x is my logarithmic factor, so I choose that to be my u. And the rest is dv. And the rest, if this is u, 1 dx is dv. differentiate ln x and I get 1 over x. Now maybe you can see why logs, right, are your first choice for you, because look what happens when you differentiate ln x. You get 1 over x, a rational function, a nice one. Same thing with inverse trig. Think about things like inverse tangent, even inverse sine and inverse cosine. You don't have inverse trig anymore. As soon as you differentiate, you've got a rational function, or at least one, with a radical when you have inverse sine and inverse cosine. Take dv, anti-differentiate this, and be careful. While the derivative of x is just 1, the antiderivative of x is not. The antiderivative of x, of 1, is x. Now, I do technically have plus c's, but I'm going to wrap all my plus c's up at the end. Substitute. Remember that this is really equal to this is my u dv, and u dv by proof is equal to uv minus the integral of v du. Be careful down here, this is not ln of x squared, this is ln of x times x minus the integral of, hello, x times 1 over x is just 1, so I'm just anti-differentiating 1 again. And I get x ln x minus the antiderivative of 1, which is x, plus my c. You can always check the work by differentiating. All right. Back to an integral that is obviously a product. Again, you run through your choices. Oh, can I do u substitution if u is x squared? The derivative is 2x. Nope. What about ln x being u? The derivative is 1 over x. Nope. So since I have a product that I can't unproduct anyway, I'm going to try integration by parts. I've run through Lipit, and the first thing I see is that I do have a logarithmic factor, so that's going to be my u, and everybody else is going to be dv. Take the derivative of ln x, I get 1 over x, anti-differentiate x squared and get x cubed over 3. Remember, this is u dv. Which by proof is equal to uv minus the integral of v du. Substitute, notice that I took the 1/3 over here, which would be inside the integral here, and osmosised it out. X cubed over x, hello, is x squared. Now, if I'm doing my work, long answer, I'm pretty tempted to leave my answer like this. Maybe I'll multiply the 3 times the 3 and get the 9. If I see multiple choice, if I'm doing a multiple choice problem, I will just kind of clean it up until I match one of the answers. So here I factored out, a 1/3. Big deal. Example 4. Another product. Looks kind of scary with cosecant squared. But, again, cosecant is trig. It's not inverse trig, right? It's just trig. I mean, it's a reciprocal function, but it is not inverse. So this is not going to be my u. I don't have a log function. I don't have an inverse trig function. I have a polynomial. So my x to the first is going to be u, and everybody else is going to be dv. So I now have the integral of u dv, which is equal to uv minus the integral of v du. So my u is my x, differentiate x and I get 1, anti-differentiate cosecant squared, and I get negative cotangent x. Substitute, float my negative out front there, x times cotangent x, and then this negative, right, was part of my v, I osmosised it out and turned the negative sign positive. The antiderivative of cotangent x is just on my list, natural log of the absolute value of sine x plus c. Ta-da! I gotta find this song for you guys. Alright, example 5 looks pretty standard. Again, in my polynomial function, x squared, I pick first. Everybody else is dv. Differentiating x squared, 2x. Anti-differentiate e to the x, and I get e to the x. Yay. Substitute. And when I substitute, a little bit of a dagger. Because after substituting, I have an integral of another product. Now remember at the very beginning when I told you that u, a good choice for u, is something that can differentiate to 0. Remember first, second, third derivatives? Look at my original u. It's x squared. The first derivative is 2x. What would the next derivative be? X squared, x to the first, you got it, x to the 0, which then, taking the derivative of a constant, would eventually get me 0. That's what I mean about differentiating to 0. So let's see how that situation helps me out. I have to use integration by parts again, which is a little bit of a bummer. Now, don't forget about this. All of this is still there, and my negative sign. So this time I go to the second integrand and I start over again. Polynomial function is going to be u, and there's dv. Differentiate x and get dx. Differentiate, anti-differentiate e to the x, still get e to the x. So now here, this just stays. My negative and the 2 still stay. This was u dv for the second piece. So this is now u v minus the integral of v du. So I'm going to have x times e to the x minus the antiderivative of e to the x. Notice no product anymore. Turn that frown upside down. Clean it up. I've got a bunch of x's and e to the x's. I'm going to leave this alone unless I'm matching multiple choice, and then I might look to pull out a common factor. So let's try another one kind of like that. Polynomial before trig, right? I have an x squared and a cosine x. I have a polynomial factor. And I have a trig factor. So since the polynomial comes first in Lipit, that's going to be my u dv. Do you see myself? Do you see where we're going to run into the same situation? U dv still ends me up with a product when I replace the integral of v du. But since again u is something that is going to differentiate down, if you know what I mean, as opposed to, you see what the deal is here, right? Cosine and sine, if you were differentiating those, or anti-differentiating, but if cosine had been our u, we'd be going back and forth and back and forth and back and forth. So here's the first run through, integration by parts, and here's going to be the second run through. Imagine this is a bit of a bummer if I had given you x to the fifth or something like that, right? Boo. These are staying from the first round, and this is the second round of IDP. So the integral of u dv is u times v, negative cosine, here's my negative, minus v, the integral of v, there's cosine, which had a minus in front of it, osmosis, du, which was 2 dx, osmosis the 2 out here, cleaned everybody up. Distributing this negative here gave me my positive 2x cosine x. Distributing this negative here gave me negative 2 times the antiderivative of cosine x, which is sine x, and then my plus c. Phew! Only if you make me. In other words, if I need to match multiple choice, will I go that far? So there you go with integration by parts. There is more to integration by parts, especially in a foreshadowing would be those questions that or the integrands where I have higher order polynomials with trig or e to the x. And I'll do that with you on Monday. But to finish out today, again, I hope you had some fun in the snow. And OPP. You gotta look it up. Naughty by Nature. Have a great one.